Welcome to the lecture series on digital electronics 18EC302C. In today's lecture, we are going to introduce Boolean algebra and postulates in Boolean algebra, and also will introduce the logic gates, basic logic gates in this session. So first we look at the topic Boolean algebra and postulates. So what is Boolean algebra and what is its importance? And for what purpose it is used. So basically Boolean algebra means it's a set of rules like a normal algebra. It's a set of rules and laws and theorems by which all logical operations can be expressed mathematically. So that means when you want to express the mathematical relation, you will be using the rules and laws and theorems of the algebra. In the same way, in order to represent or express all the logical operations that actually uh, happen inside the digital circuits and systems, you also require a certain different type of algebra called Boolean algebra. And this Boolean algebra comprises of set of rules and laws and theorems which can be used to express the various functions of the digital circuits in a mathematical way, so that the mathematical expressions can be manipulated to obtain to minimize to see the functions of digital systems. So basically Boolean algebra defines a set of elements which are allowed and a set of operations which operate with the elements and a set of postulates. So basically, in parallel with the normal algebra rules and normal algebra, so it also has set of elements on which the Boolean algebra laws and theorems are rules and defined, and we also have a set of operations which operate on the with the elements, and we also have the set of rules, and basically we have set of assumptions, and these assumptions which are assumed to be true are called as postulates, and that basic postulates will be discussed now. So postulate means here um, is the assumption, it is a rule or law which is assumed to be true, and based on these postulates we will form certain theorems, and by using all these rules, laws and theorems we will define the Boolean algebra is defined, and this Boolean algebra can be used to express the functions mathematically, or functions of all the digital circuits and systems mathematically. So here we'll start discussing the postulates. So for this we'll look at the certain notations before going to discuss the actual postulates. So postulates is defined, the Boolean algebra is defined on a set of elements, and it also defines set of operations, and it also defines set of rules that are assumed to be true. So here also we'll assume the same thing. If M is used as a set and if xy are the two objects, then we'll be using certain notation that xy belongs to M implies that xy are the members of the set M. That means xy are the elements of the set M, or xy are the members of the set M. And similarly, y doesn't belongs to M means y is not a member of the set M. So these are the notation that we will be using when we are defining or when we are discussing the postulates. So next we look at the postulate number 1. So here this postulate defines two operations. The first one is logical addition, and that is defined with the symbol plus. But this plus is different from the normal addition operation that is defined in the algebra. So it is plus defines mathematical addition in normal algebra, and here it represents logical addition. And we'll see how it is different from the normal addition symbol in the algebra. So postulate 1 defines the operations, the two operations. First one is logical addition, and second one is logical multiplication. So here it defines that an operation plus logical addition is defined such that if z equals to x plus y, so here it is defined as not exactly as plus, it is defined as OR operation. So z equals to x or y, then z belongs to the set M, or every pair of the xy belongs to M. So that means if you take any two elements xy which belongs to the set M, then if you perform OR operation between those two elements, and the result also belongs to the same set. So this is how the OR operation or logical addition is defined. Similarly, we will define one more operation called logical multiplication. So here it is stated as an operation. So this is called AND operation. So an operation logical multiplication or AND is defined such that if z equals to x dot y, then z belongs to the set M for every pair elements xy belongs to M. So here it means that for a pair of elements xy belongs to the set M, if you perform the AND operation or logical multiplication between those two elements, the result Z also belongs to the same set. And this is how the AND operation is defined, or logical multiplication is defined by postulate 1. So here postulate 1 defines two boolean operations or two boolean operator. One is boolean operations or operators, one is OR operator, and the second is AND operator or logical addition operation and logical multiplication operation. So this is what the postulate 1 defines. And postulate 2 defines two elements. So postulate 2 defines two elements. One is element 0, another is element 1. So here the first definition of postulate 2 stated as there exists an element 0 in the set M such that x or 0 equal to x for every x belongs to M. So element 0 is defined such that for any element x that belongs to set M, if you perform OR operation between the element and element 0, then the result will be the element itself. So this is how the element 0 is defined. And postulate 2 also defines one more element, and it states that there exists an element 1 in M such that x and 1 equal to x for every x belongs to M. So this means that for any element x that belongs to the set M, if you perform an AND operation with the element 1, it results in the same element. and this is the way how we define the element 1. So postulate 2 defines two elements. One is element 0 and element 1. So far postulate 1 defines two operations and postulate 2 defines two elements, and postulate 3 defines states the law called commutative law commutative law and he postulate 3 is stated as it states commutative law for both OR operation and AND operation between the two elements, and the statement goes this way: for x y belongs to the set M, the following commutative law holds. So for any two elements that belongs to the set M, the commutative law holds. So that means if you apply this commutative law for OR operation, then x or y equals to y or x. So this also means that the OR operation gives the same result irrespective of the order of the elements on which it is performed. So even if you change the order of elements, uh, the OR operation gives the same result. And similarly, the commutative law is also defined for the AND operation. So that is, though you change the order of the elements on which you are performing AND operation, it results the result is the same, that is x and y equals y and x. So either way, so we can perform the operation of AND operation of y with x, or we can also perform AND operation of x with y. So the result of both will be same, and this uh, is called commutative law, and it is applicable for both operations that we defined in the postulate 1, that is both OR operation and AND operation, or for logical addition and for logical multiplication also. So postulate 3 defines one law called commutative law, which holds true for both the OR operation and AND operation between any two elements that belongs to the same set M. And postulate 4 states one more law called distributive law. So here the distributive law states that either the OR operation or AND operation can be distributed over the AND or OR operation respectively. So what is this means? So here we have shown that there are three elements x, y, z belongs to the set M, and then the distributive law holds for both AND operation and OR operation. So the first statement states that the here the expression tells that AND operation is performed between x and the other element, which is uh, y or z. So now this AND operation can be distributed over this OR operation. So that means so this so OR operation is performed first, that is between the two elements y and z. So y or z, and after that it is AND operation is performed between this result and x. Now this AND operation can be distributed over this OR operation. So then it becomes x and y and x and z, and these two results must be ORed. So x dot y plus z equals x dot y plus x dot z. And similarly, so this is distribution of AND operation over OR. So similarly, the OR operation can also be distributed over AND operation. So here you can see that the AND operation is performed between the two elements y and z, and OR operation is performed on the result and the element x. So this is same as AND operation is performed between the result of XOR y and XOR z. So here the OR operation is distributed over AND operation. So x r y dot z equals x r y dot x r z. So this is what the postulate 4 defines the distributive law. So the distributive law holds good for AND operation distributed over OR operation, and OR operation distributed over AND operation. And coming to the next postulate, postulate number 5. The postulate number 5 defines the complement of a certain element. So for every element x that belongs to the set M, there exists an element x cap or x complement such that the OR operation performed between the element and its complement equals 1, and the AND operation performed between the element and its complement results in 0. So this is how the complement is defined by postulate 5. So whatever will be the element, if you perform the OR operation between the element and its complement, the result is 1. And if you perform the AND operation between the element and its complement, the result is 0. So this is how the complement of a particular element is defined. So we are left with one more postulate, postulate number 6, and this defines that the distinct elements of the set. So here it says that there exist at least two elements x comma y that belongs to set M such that x not equals y. So postulate 6 simply defines that there must be at least two distinct elements in the set M, that is on which the Boolean algebra and its postulates and operations and elements are defined. So there must be at least two elements x and y such that they are different. So this is what the postulates defined for the Boolean algebra. And here you can see that basically Boolean algebra means set of rules, laws and theorems by which we can express the functions of the digital circuits systems in a convenient way. And to define these functions, we require certain elements and certain operations, and we require certain set of postulates or rules and theorems, and for that we define the 6 postulates which are assumed to be true, the rules which are assumed to be true. In the postulate 1 we define the two operations AND operation and OR operation. In postulate 2 we define two elements on which these operations can be performed, that is element 0 and element 1. And postulate 3 defines the commutative law for both AND operation and OR operation. And postulate 4 defines distributive law for both AND operation and OR operation. So AND operation distributed over OR operation, and OR operation distributed over AND operation. And postulate 5 defines the complement of an element, and postulate 6 defines that there must be at least two elements in the set such that x not equals to y, and xy belongs to M such that x not equals y. Next, so this is about the Boolean algebra and the postulates, and next we'll look at the logic gates. In particular, we'll look at the basic logic gates. So what is a logic gate? So before going to see actual logic gates, so we'll define and we'll see what is a logic gate and what is the use of the logic gate, and how it is represented, or how to interpret the relation of its inputs and outputs. So basically a logic gate is an electronic circuit which makes logical decisions by manipulating the information given at its input. So it's a circuit. It's a circuit basically. It's an electronic circuit, but it's a decision making circuit. Okay, decision making circuit. So it makes only logical decisions. That is input and output. So the output will be either 1 or 0. So since it is a decision circuit, the input for the circuit is also in binary format. So we can define the logic gate electronic circuit for which we will give binary information as its input, and the output is also binary. That means the output is either 1 or 0. So the circuit makes a logical decision based on the information, binary information given to it. So it processes the binary information and gives output as either yes or no decision. So basically we can say that the logic gates have two or more inputs and only one output. The output says yes or no. This is logical decision making. So we can say that the logic gate has only one output and it has two or more inputs. So then what is the relationship between the output and input? So this relationship gives the behavior of the logic gate or the behavior of the electronic circuit which is making logical decisions. So then how to represent this relationship between input and output? So one way of representing the relationship between input and output variables of the logic gate is by using the algebraic equation, and the other way of representing the relation between input and output variables of logic gate is by using a tabular form that is called as truth table. So the truth table represents all possible combinations of inputs, and for each combination of inputs it shows what is the value the output variable is. So overall the truth table gives the overall behavior of the logic gate. It includes all the input combinations that can be applied to the circuit, and for every combination of the input at input level the corresponding output produced by the logic gate. So the truth table is a tabular form of representation of the behavior of logic gate, and we represent use boolean algebra, then the same behavior can be represented by an algebraic equation. And since we are saying that a logic gate is an electronic circuit, and it consists of a number of transistors and certain number of circuit elements and capacitors and power supplies and everything. So logic gate is very small building block of the digital circuit or digital system. So we'll be using a logic gate, certain number of logic gates repeatedly a number of times to make a very large digital circuit or system. So to represent that electronic circuit, we'll be using a distinct symbol for distinct electronic circuits. So each logic gate we see has a distinct symbol called logic symbol. So every logic gate has its own logic symbol. And so what are the various electronic circuits that can make logical decisions? Are that what are the various types of logic gates that we have to build the digital circuits? So here goes the list. The first set of logic gates are AND logic gate, OR logic gate, and NOT logic gate. And these are the logic gates which are used to perform the basic operations that we defined earlier in the postulates. So for example, AND logic gate performs the AND operation, and OR logic gate performs the OR operation between any two elements, and the NOT logic gate performs uh, the complementation operation for any element. So these are the three logic gates which which perform the basic operations that are defined on the elements of the boolean elements of the boolean algebra. Then these three gates are called as basic logic gates. And apart from these three basic logic gates, we have few more logic gates. The second set is NAND logic gate and NOR logic gate, and due to their special property, they are called as universal logic gates or simply universal gates. And we have a third category, that is XOR logic gate and XNOR logic gate. So these logic gates can be constructed using basic gates, so they are not exist directly as a separate circuits, but they can be constructed using basic gates, and their functionality can be obtained by using the constructed circuits. So basically here, summarizing this slide, The logic gate means an electronic circuit which will make decisions, and the decisions means it's the output of yes or no. And so that means a logic gate has two or more inputs, but it has only one output. And the relation between these inputs and outputs can be either expressed by using an equation called algebraic equation or boolean equation, and it can also be expressed in the form of a table, and that is called as a truth table, where the truth table lists all possible combinations of the input and the corresponding output produced by the logic gate or the logic circuit. And since we will be using the logic gate as the basic building block, so each electronic circuit or each logic gate is given a logic symbol, so which will be used to construct a very large digital circuits. And we have a number of logic gates here. So those logic gates are AND gate, OR gate, NOT gate, NAND gate, NOR gate, and XOR gate, and XOR gate. So out of this, AND, OR, and NOT gates are called basic logic gates, and NAND and NOR are called universal gates, and XOR and XOR are called are basically constructed using the basic gates AND or NOT. So next we will discuss about the basic logic gates. So first we'll look at the OR gate. So the OR gate is an electronic circuit which performs logical addition between two or more elements. So for the simplicity, first we'll be considering only two elements. Here we'll be considering those two elements as A and B. So this OR gate is an electronic circuit which performs logical addition between the two elements A and B. And here I assume that A and B are the inputs and X is the output. So the OR gate in general has two or more inputs and only one output, and here I consider only two inputs, and the input variables are A and B, and the output variable I assume that it is X. So as we mentioned already, every logic gate is given a logic symbol, and this is the symbol that is given for OR gate. So this is the symbol that is given for OR gate, and this is the symbol exactly given for the two input OR gate. So OR gate means it has only one output always, and it can have two or more inputs for a general OR gate. And since it has only two inputs, and this is called two input OR gate or simply OR gate. And the input variables here, they are named as A and B, and the output variable named as X. So since this electronic circuit or logic gate performs logical addition, so then the output X is equal to A or B, or OR operation between the two input variables A and B. So X equal to A or B. So the output is OR operation between the inputs. Now the property of this OR gate is the behavior of this OR gate can be shown by using either a truth table, by showing truth table, where for the truth table, how the truth table is constructed. So in the truth table, on the left hand side, we'll show the inputs, and the inputs can be two or more in general, and here we have only two variables since this is a two input OR gate. So here we have only two variables, so write the variable names at the top A and B, and at the right side will show the output. So we have here we have written x is the output variable, and by boolean equation we say that x is equal to a or b. And so what a truth table will show all possible combinations of the inputs. So here we have two input variables or two inputs, and it shows all possible combinations. That means in one case a can be 0 and b can be 0, and in other case a can be 0 and b can be 1, and in some other case a can be assumed logic 1 and b can assume logic 0, and in some other case a can assume 1 and b can assume 1 also. So this part gives all possible combinations of the input variables. So here a can assume either 0 or 1. At the same time, when a is assuming 0, b can assume either 0 or 1. Similarly, a can assume 1, and when a is assuming 1, b can be either 0 or 1. So this part gives all possible combinations of the input for the logic gate. And coming to the right side part, so here x is the output variable, and here for each combination of input this part shows the corresponding output given by the logic gate. So here if you take the first case where a is equal to 0 and b is equal to 0, then when two inputs are at logic 0, then what will be the output of this OR gate? So this can be calculated by using this expression, that substitute logic 0 for a and b in this expression and evaluate what will be the value for x. So x equal to 0 or 0, x equal to 0 or 0, and this is similar to your normal addition except for one case that we will see. So 0 or 0 means it is 0 only. So x becomes 0 when a and b both are 0, and when a equal to 0 and b equal to 1, then x becomes 1 or 0, 0 or 1, so that also becomes 1, and when a equal to 1 and b equal to 0, x equal to 1 or 0, that also equal to 1, and when a equal to 1 and b equal to 1, x equal to 1 or 1. So here 1 plus 1 is not equal to 2, but here 1 plus 1 means 1 or 1. So here it is equal to 1 only. So this is how the behavior of the OR gate can be shown as a truth table, where the left side elements indicate the input variables and the right side elements indicate the output variable. So the output variable is only one, because for all logic gates the output is only one, because all of them are decision making circuits. So overall, if we observe the truth table for this OR gate, we can see when for which combinations of the input the output is becoming 0, and for which combinations of input the output is becoming 1. You can clearly observe that output is 0 only when both a and b are 0, or I can also say that the output is 1 when any of the input is equal to 1. So if either b equal to 1, output is 1. If a equal to 1, output is 1. Or if both a and b are 1, then also the output is 1. So the output is 0 only in case when both inputs are 0. So this way also we can define the behavior or the operation performed by logic gate OR. So here the operation is such that a high on the output is produced. A high on the output is produced when any of its input is high, and the output is low only when all the inputs are low. So this gives the behavior of the operation performed by OR gate and its logical symbol and its behavior expressed as a boolean expression or boolean equation x equal to a plus b, and its behavior represented by a table called truth table. And here goes the logic gate number 2, the basic logic gate, the AND gate. So AND gate performs a logical multiplication. The operation performed by AND gate is logical multiplication or AND operation. So the AND gate also has two or more inputs and also has only one output, and here also we assume that the input variables are given the names A and B. The output variable is given the name X, and here also you can see that this is the logic symbol given for AND gate. So the inputs are shown here A and B. So since inputs can be two or more for a general AND gate, and here we have shown only two input AND gate which has only two inputs A and B here, and the output is always only one output, and here the output is shown with the variable X. So X equal to, since it performs logical multiplication, X equal to A dot B. Actually dot can be ignored sometimes, and it can be simply written as X equal to AB, or more accurately X equal to A dot B. So this behavior or the operation performed by this AND gate and logic gate can also be shown by using truth table. So here's the same thing. The left side of the truth table shows the input variables A and B and all the possible combinations for the input variables. That means when A assumes 0, B can assume either 0 or 1, and when A assumes 1, B can assume 0 or 1. And the right side column shows the output variable, and output variable x equal to A and B, or A dot B. So you can substitute for each combinations of the inputs. You can find out, calculate what is value of x by substituting those two bits into this equation, boolean equation. So x, when A is 0, B is 0, x equal to 0 dot 0, or 0 and 0, which is 0. And when A equal to 0 and B equal to 1, x equal to 0 dot 1, so that is also equal to 0. When A equal to 1, B equal to 0, x equal to 1 dot 0, that is also 0. When A equal to 1, B equal to 1, x equal to 1 dot 1, 1 and 1, so that is also equal to 1. So here you can see and observe, drawing a conclusion from the truth table, that the output of the AND gate is 1 or it is also called high only when both the inputs are logic 1 or high. So that is the operation of an AND gate is such that a high on the output is produced when all of its inputs are high, otherwise the output is 0. That means AND gate produces a high output only when all of its inputs are high. Otherwise, even if one of the input is 0, that is this case, or if both the inputs are 0, that is this case, the output will be low. So this is the operation performed by the AND gate. It performs logical multiplication, and this is how the inputs and outputs are related by shown as a truth table, and this is how the input and outputs are related shown by boolean equation, and this is the logic symbol given for the AND gate. So we have one more basic logic gate, that is called as NOT gate. So here NOT gate performs a logical function called complementation. That means so NOT gate here is a very one special feature is that it has only one input, and like all other gates it also has only one output. So but the input is one always. So you cannot give two inputs for an OR gate, NOT gate. So whatever the input that you give for NOT gate, the output produced by the NOT gate will be complement of the input. That means if you give the input as X, the output will be X bar, right? So here we have shown the logic symbol for NOT gate, and this presence of this bubble small circle always denotes that inversion or complement operation. That means the output, so here the input variable is defined with the letter A, and the output variable is defined with letter X, and since it performs complement operation, the output will be, since input is A, the output will be A complement, A bar or A complement. So output X equal to A complement. So this small circle always indicates that there is inversion between output and input. So this can also be shown by using a truth table. So the truth table contains, again, the left side contains the input variables, but here there is only one input variable, so it shows A as input variable, and the right hand side the output variable is shown where it is X, which is equal to complement of A, and on the left side for the input variable it gives all combinations that input variable can assume. So since it is a binary variable, it can assume only two values, one is 0 and other is 1. So for each case the truth table gives what is the output. So when A is equal to 0, X becomes 0 complement. So 0 complement means X becomes 1, and when A equal to 1, X equal to 1 complement, that becomes 0. So here when a high level is applied at input as an input, a low appears at the output and vice versa. And since NOT gate performs the complement operation, whatever the input that you give, the output will be complement or the inverse of the input. So these are the three logic gates. We have indicated the operation performed by all the three logic gates respectively, and their behavior or the operation performed by all the three gates described as in the form of truth table or in the form of expression, and the logic symbol given for each of the gate is also shown.